Welcome everyone to day 4 of the Women in Data Science Daily at Penn. My name is Zhao, a professor in Wharton Statistics Department. It is my pleasure to chair this session. For the second year, the WiDS at Penn 2021 is organized jointly by the Statistics Department, Penn Engineering School, Wharton Customer Analytics, and Analytics at Wharton. Women in Data Science Daily at Penn is an independent event presented by the University of Pennsylvania to coincide with the annual Global WiDS conference held at Stanford University and an estimated 150 plus organizations worldwide. This year, as you can see that the WiDS at Penn is being held virtually as a serialized week of programming. Every day of this week, we feature 1 hour of live broadcasting from 12 to 1 p.m. Eastern Time. Please join us tomorrow to hear from several groups of students about their research and projects conducted. Today, you will hear from 2 young but academically giant scientists and experts in the field of data science, followed by live question and answer during the second half of this broadcast. Networking will take place for 30 minutes after this live session in a cool virtual gather time. Check it out if you haven't done so. We look forward to see you there. So we are so thrilled to have Sandra and Danielle with us today. The theme of the year, of this year's WiDS is what a data scientist looks like. Perhaps we really mean how they become a data scientist. What do they do? And I'm going to take this opportunity to tell you a little bit about each one of them. Let me start with Sandra. Sandra González-Bailón is an associate professor at the Annenberg School for Communication. She has a sociology PhD from University of Oxford. Her research lies at intersection of network science, data mining, computational tools, and political communication. Still in her early stage of career, Sandra is already a rising star with numerous high-quality and highly cited publications. In her recent book, Decoding the Social World, she demonstrates how data science and analysis of a network help us solve the puzzle of unintended consequences. Sandra leads her research group, DimeNet, please check that out from her website, which focus on digital media, social network, and political communication. They analyze how people interact, communicate, and organize via the lens of online behavior. Social media has created new information channels. Well, in the good old days, the traditional media was our main source of information. For example, well, young people, you know more than I do. Twitter has 300 million users and 500 million tweets are sent out daily. Who are the owners of these accounts? Do you know behind these accounts, some of them are robots instead of human beings? Take a look at the slide I put here. Each one of them really looks like a real person and sounds like they each owns a real account. But in fact, no, they are bots, robots. So there are 50 million Twitter bots currently, and 15% of the tweets are done by bots. I took those numbers very quickly from internet that I hope the discrepancy is not too far. So today, Sandra will talk about identifying the influence of automated accounts, that is bots, on social media, using tools from network science, natural language processing, and machine learning. So next, let me talk a little bit about Danielle Bassett. Danielle Bassett is a J. Peter Carnish Professor, sorry if I don't say it quite right, with primary appointment in the Department of Bioengineering. And she also has quite a number of secondary appointments at Penn and elsewhere. By training, she is really a physicist. She has a PhD in physics from University of Cambridge. What a coincidence that the two ladies are all trained in England. Among numerous awards, right, any single one of them is very significant, but I'm going to only just pick up one. She was the youngest individual to be awarded a 2014 MacArthur Fellowship. I estimated, I think she was then around 34 or 33, around there. She is an outstanding example of interdisciplinary scientist, most well known for blending neural and system engineering to identify fundamental mechanisms of cognition and disease in human brain networks. Danielle leads her complex system lab with large number of postdocs, PhDs, and undergrads. And she is actively recruiting, so please check out her website. She is extremely productive that if you look at her 67 long page of the CV, you won't be surprised that she has published 312 papers with 45 submitted and another 20 papers being prepared. She is extremely highly cited. As of last night, the Google citation was 26,951. She is writing a book, Curious Minds, with co-author Perry Zern. We're really looking forward to her book. Thinking about curiosity, we're also curious about how we learn the world. So in today's talk, Danielle will show us how to use her beautiful network models to explain how humans build models of the world. Without further ado, let me turn the screen to Sandra and Danielle. See you later in Q&A session.
Well, so my purpose for today's talk is to tell you a little bit about one of my projects in which I try to identify the influence that automated accounts or bots have on social media, and in particular on the information that circulates through those networks. There is going to be 3 parts in this talk. I'm going to start outlining the motivation for this research. I will then give you more details about the data and the analysis. And I will finish with the so what question, that is why we should care about this research and its findings. Motivating this work, there are essentially 2 questions. One is about the prevalence of bot activity in online interactions and political talk. And the second is about whether traditional media are still playing a gatekeeping role in the information that circulates online. This research is part of a broader agenda in which I try to understand the consequences of having transitioned from the era of broadcasting, when the number of news sources were limited and most citizens were exposed to the same information, to the current era of network communication, which is characterized by a long tail of media options and by rising fragmentation in the supply of news and information. Now, many accounts suggest that this increased choice leads to audience fragmentation, ideological segregation, and echo chambers with no cross-cutting exposure. And some of my work tests some of those assumptions. But today, I'm going to pay attention to how those new forms of network communication are being used to coordinate and organize collective action, and to the question of whether bots are trying to hijack those collective action efforts to spread their own information. The context in which I evaluate the influence of bots in this project is given by two episodes of contentious politics. One is the Yellow Vests movement that erupted in France at the end of 2018 to demand economic justice. And the second is the mobilization around the Catalan referendum for independence from Spain, which took place in October of 2017. These two events were widely covered by mainstream media, nationally and internationally, but they also generated high volumes of social media activity, with Twitter first channeling the news that were coming out of street actions and confrontations with the police. According to journalistic accounts, and you have a few example headlines on the screen, Twitter helped fuel political feuds by enabling bots to exacerbate conflict and allowing foreign interference in the dissemination of false information. Now, of course, it is not the journalistic practice to provide the same level of empirical evidence as we researchers require, so this project was designed to test many of these claims. We know that online networks carry benefits and risks with high-stakes consequences during contentious political events like the two mobilizations that we consider. They can be tools for organization and awareness, or tools for disinformation and conflict. So what this research does is compare the attention that bot accounts receive during these events of intense political mobilization with the visibility of mainstream verified media accounts. And in particular, we want to determine if there was a discrepancy in the visibility and reach of news sources on Twitter compared to what was happening elsewhere on the web. And the web creates an information ecosystem in which bots do not have much say. And if we do find evidence of discrepancy, we want to determine if bot activity helps explain it. If some sources of information are more visible on Twitter than they are on the web in terms of reach, it could be because bots are retweeting those sources, and these sources would be much more peripheral otherwise, which is something that these headlines seem to allude to. So I'm going to tell you now about the data and the analysis, and the summary is this. We combine Twitter data and web tracking data to measure and compare the visibility of news sources on these two channels. The core of the analysis is about contextualizing the role of social media as an entry point to news. But for this, we need to first identify automated accounts or bots, which requires using machine learning classifiers. We also need to account for the content of the messages of the tweets, for which we use natural language processing. And we need to measure centrality in the diffusion of information, for which we use network science tools. And for those of you who are impatient to know, our analysis do cast doubts on the impact that bot activity had on the coverage of these mobilizations. What our findings suggest is that verified blue badge accounts were significantly more visible and central during our events. And because talks like these only allow you to say so much about data and methods, for those of you who are interested, you can find the paper online with a more thorough description of everything that I'll mention today. So this is a first take of the data that we're analyzing. We collected the data through Twitter's publicly available API by retrieving all messages that contain at least one relevant hashtag for each of the two mobilization events. In total, we collected more than 1 million tweets sent by hundreds of thousands of unique users. We used bot detection techniques to identify automated accounts, and we also used the verified feature to identify the accounts that the platform recognizes as being of public interest. Accounts that exhibit bot-like behavior but that are also verified by Twitter include news organizations, journalists, and public figures. And this is a category that we label with the shorthand media. So what you can see in this figure is that in both data sets, only a small fraction of all accounts involved in spreading information around these two mobilizations, and that's less than 1%, fall in this media category. About 4 in 10 are classified as unverified bots, and about 6 in 10 are classified as human. This figure gives us a little bit more information on longitudinal changes in the volume of Twitter messages. Panels A1 and A2 show totals in messages posted and retweets received by the 3 types of accounts, media, bots, and humans. During the Yellow Vests protests, panels B1 and B2 show the same information during the Catalan referendum protests. In general, the ratio of messages sent by each of these 3 types of accounts does not change drastically over time, and the peaks correspond to the dates of massive mobilizations on the streets. Retweets are essential for the argument that we make in this paper because retweets are the main mechanism of information diffusion on the platform. The networks of retweets that we build with this data, however, are too large to visualize in full, and so what you have on the screen is a summary version of these networks. These are the top 10 largest communities. Every node represents a community, which in network talk means a subset of the network where connections are denser internally than externally, or in other words, the individual accounts within each community are retweeting each other more frequently. And so what we see here, first of all, is that media accounts are barely visible. There is very few of them, as we have already established. But second, we also see that human accounts and unverified bots are frequently retweeting each other. There is no clear evidence of clustering by account type, and so there's a lot of co-exposure to what bot accounts are posting on Twitter and what human accounts are posting on Twitter. Here we explore another aspect of the network, and that's the levels of reciprocity, or where reciprocal ties lie. And what we see is that this network is very asymmetrical and hierarchical, meaning there is only a small number of retweeting connections that get reciprocated. But when these ties exist, they mostly connect human accounts. And this matters because one of the ways in which bots fool humans is by pretending that they are human as well. And so if we take reciprocity as a proxy to closeness or engagement, then most of that engagement still happens between human accounts. If we look a little bit more systematically at the centrality distributions in these networks by account category, what we see is that in spite of being a minority, media accounts are significantly more central than we would expect by chance in both mobilizations. We also see that humans are significantly less central than we would expect, and that bots are generating many of the retweets granting centrality. And so what you see here, the box plots summarize the values obtained from permutations of the data where the category labels are randomly reshuffled. And so departure from randomness means that the observed values fall outside the permutation box plots. Now, everything that I've discussed so far derives from the Twitter data set. As I mentioned before, we also analyze web tracking data, and in particular, we look at the audience reach of media sites on the web. Percentage reach refers to the fraction of the online population in France and in Spain, respectively, that access a given media site during the period in which these mobilizations took place. And so essentially, this figure allows us to identify the news sites that acted as the main sources of information online during the mobilizations. One of the things that we see is that news consumption is more concentrated in France, and it is also a less frequent activity among the online population. Only 5% of all news sites have an audience reach of 13% or higher, with a maximum of 41%, which means that less than half of the online population in France were consuming news on the web in this particular time period. In Spain, only 5% of all news sites have an audience reach of 32% or higher, with a maximum of 66% for the most read newspaper. And these numbers suggest that the overall levels of user engagement with digital news is not that high or evenly distributed. In any case, what matters here is that with this data, we have a ranking of legitimate news sources ranked according to their visibility and audience reach. And so our next question is, do these sources also attain similar visibility on Twitter? Here we have the correlation of rank position in percentage reach on the web and retweet centrality. The scatter plots on the left column measure the association between audience reach on the web and number of followers on Twitter, but the more interesting scatter plots are on the right, and they measure the association of reach with number of retweets received in the stream of information specifically related to the protest. And what we see is that the correlation is rather weak. So the most accessed news sources on the web are not the most salient in the Twitter stream covering the mobilizations. And this begs the question, are bots responsible for this discrepancy? This is the question that this figure aims to answer. Here we look at whether the difference in visibility rankings correlates with the number of bots retweeting those sources. And we do this by looking at the neighborhood in the retweet network of these media outlets. Outlets above the zero line have better ranking on Twitter. Outlets below the zero line have better ranking on the web. And the horizontal axis measure the number of unverified bots retweeting these outlets. And as we see, there seems to be a moderate correlation, meaning that the more bots are retweeting these sources, the higher the discrepancy of the Twitter visibility is. But once we control for the size of the neighborhood, in other words, once we control for the presence of human accounts also retweeting those sources, the correlation disappears, meaning human accounts are also responsible for generating this discrepancy. We also wanted to take into account the nature of the messages tweeted and retweeted, and we did this by quantifying the sentiment of each tweet. And so for this, we used a well-established natural language processing technique that is specifically designed to analyze sentiments expressed in social media. By design, the original version of this technique is built to analyze English text. And so we modified it to support sentiment analysis of text that also includes Spanish, Catalan, and French. This figure shows the distribution of this, which means extremely negative sentiment, to +1, which means extremely positive sentiment, with 0 values representing neutral messages. And so with this information and all the other information I already discussed, we used mixed effects models at the message level to identify the factors that predict the number of retweets that messages received during these protests. Messages are nested within unique users, so we use account ID as the random effect, which also allows us to control for unmeasured characteristics at the user level. Our fixed effects include 3 controlled variables: number of followers, number of friends, and the sentiment score of the messages, and 2 explanatory variables, namely whether the account posting the messages is classified as media or as human, with bots as the base category. As a robustness test, we fitted these models with and without neutral messages in the data. So remember, those are messages that have a sentiment score of 0, and with and without a binary variable identifying accounts that are also present in our web tracking data. So these would be the legitimate news sources. And these figures show the results. Controlling by structure and content and random variability at the account level, messages published by media accounts receive more retweets than messages published by unverified bots, which is the base category, but also messages posted by human accounts receive less diffusion. Controlling for all these things, the subset of news organizations for which we have web tracking data also receive less attention than verified media accounts. And this is an effect that is particularly strong during the Catalan referendum, and it highlights the power that social media has to challenge gatekeeping, traditional gatekeeping roles. So let me step back now and give a summary of what this all means. First, we show that verified accounts are more likely to receive retweets and therefore that they were reference points in the coverage of the mobilizations. Their messages actually received more attention than news outlets with sustained traffic on the web. And we also show that bot activity is not responsible for creating discrepancies in the visibility of news outlets. If anything, human retweeting is more important in amplifying differences of visibility in social media compared to the web. Based on these observational data, it is not possible to determine if these interactions and types of exposure had any effects on opinions and attitudes. And likewise, it is also difficult to determine if exposure to other media content on the web, or more generally in the wider news ecosystem, can counteract the effects of exposure on Twitter. However, we do find little evidence that bots manage to gain comparable prominence to verified media accounts. These findings also highlight the importance of clearly defining the policies that underlie the verification process of social media accounts. There is abundant evidence that misleading information is often spread from verified accounts, including those of government officials and recognized public figures. Verified accounts have also amplified the messages of dubious sources that would be fringe and less visible otherwise. And so what our results suggest is that we need to pay more attention to the complex relationships that emerge in the interactions of verified accounts with other user accounts, because in the end, effective disinformation campaigns involve a range of different participants, and the actors behind those campaigns work around platform policies, including public verification programs. More generally, given the impact that misinformation can have on democracies, it is important to understand the role that bots play in the dissemination of news, especially in the context of contentious political events, which are particularly volatile and susceptible to misinformation. However, it is also important to contextualize the role of bots in the broader media landscape. Social media, at the end of the day, is just one layer of communication in a much more complex media environment. And this takes me to my last slide, which is about next steps. So what's next? How can we push this research area further? Well, one of the big difficulties we confront today is not only that the media landscape has become way more decentralized than it used to be. It is also that information is flowing through all these parallel channels, the web, social media, TV, radio. And not only are we far from measuring in accurate and reliable ways exposure in each of these channels, but we are even farther from understanding spillover effects. Only about 20 to 25% of the online population is on Twitter, but journalists are overwhelmingly on Twitter, and whatever happens on Twitter will percolate to what we watch on TV or what we read in our traditional newspapers, and we are far from understanding those dynamics. The other big problem is not so much what digital technologies do to our news exposure, but how they allow us to opt out. And this is the choice that a large fraction of the online population seems to be making. One of the priorities to my mind for future research is to look at this huge chunk of the online population that do not seem that interested in legitimate news, and ask, so where are they getting their information? And are they more vulnerable to misinformation campaigns and manipulation efforts? And to answer this question, the bottom line is that we still need to do a lot of work, but we are already doing it, and I'm going to leave it here.
I'm very happy to be with you all today to tell you about some of our work in how humans build models of the world. And I'm really excited to give this talk in support of all gender minorities in data science, including cisgender and transgender women, transgender men, and gender fluid and non-binary people. So first, I want to start with the question of what is knowledge? From Henri Poincaré's 1905 Science and Hypothesis, he writes, "The aim of science is not things themselves, as the dogmatists in their simplicity imagine, but the relations among things. Outside these relations, there is no reality knowable." And John Dewey, in his 1916 Democracy and Education, writes, "Knowledge is a perception of those connections of an object which determine its applicability in a given situation. Thus, we get at a new event indirectly instead of immediately by invention, ingenuity, resourcefulness. And ideally, perfect knowledge would represent such a network of interconnections that any past experience would offer a point of advantage from which to get at the problem presented in a new experience. So what these two quotes indicate is that knowledge is a network of some kind. And not only is it a network, but it's a network that can be and is learned by example. So suppose that I must translate 15 ideas to a class here at Penn, and those 15 ideas are indicated on the left-hand side. They're related to one another in a heterogeneous way. So idea 8 is not particularly related to idea 3, but idea 8 is related very tightly to idea 7. So their relationships create a network. My challenge as an instructor is to translate this network as information linearly because time is one-dimensional and unidirectional. So how do I create this information time series in a way that maximizes learning? Let's put that in pictures to make it a little more concrete. So on the left-hand side, I imagine the brain of the speaker or writer. There's a network of knowledge inside of their head, and they have to map that network into the one dimension of time by stringing concepts out so that they say one word after another or write one line after another if they're writing. And they need to do that in such a way that the brain of the listener or reader over here on the right-hand side can optimally reconstruct what that high-dimensional object was, that network. So how do we do this? How do we choose how to map a high-dimensional object into a one-dimensional space? And how does somebody who's listening reconstruct from 1D information something that's potentially higher dimensional? It's amazing that this actually happens. And I've framed this as a problem of communication in a classroom or in writing, but actually the very basic capacity to infer patterns of pairwise dependencies from incoming streams of data is what allows we as humans to learn language, to segment visual events, to parse tonal groupings, to parse spatial scenes, to infer social networks, and even to perceive distinct concepts. So it's something that we as humans do all the time, but it seems a bit like magic. So how does it happen? In order to understand how it happens, we need to build a laboratory experiment where we can show people information on a given network architecture and ask how they learn it. So the way that we do that is that we begin by allowing each node in the network to be a specific stimulus, a word, an image, or a movement. And then we allow every edge inside of the network, or one of these lines here, to indicate an allowable transition between two nodes. So I can move from idea 8 to idea 7 because those two are directly related, but I can't move from idea 8 to idea 3. That would be a non sequitur. Now what we do is that we construct a sequence of these stimuli by taking a random walk on this graph. So we could move from idea 8 to idea 10 and to 11 to 12 to 14 to 15, etc. We walk through this network, and that creates this time series, this information time series, one unit after the other. In order to see how well a human is learning the network, we ask them to perform a small task and we measure their time to react. And that allows us to see how well they are learning the network. If they respond quickly, they're learning it well. If they respond slowly, they're learning it less well. So what do we already know about this kind of problem, humans learning networks around them? Well, from the work in statistical learning and the study of artificial grammars, we know that humans are very sensitive to what are called transition probabilities. So if you're sitting in an environment where event A transitions to event B 75% of the time and transitions to event C 25% of the time, then whenever you see A, you'll expect B 3 times more than you expect C, and you're just very good at doing that. Now, an interesting corollary to that is that if you are in an environment where A only ever has 2 possible outcomes, you'll expect them both 50% of the time, and you'll be fairly confident and certain in what's happening in your world because only 2 things ever happen. But if you're sitting at A and in your environment, 3 outcomes sometimes happen from A, then you'll expect each of them 33% of the time, and you'll have less certainty. You have to prepare for 3 different possible outcomes rather than just 2 possible outcomes. You don't know which to expect most, and so you'll respond more slowly. So in simple environments, you'll respond quickly. In more complex environments, you respond slowly. So we can see this by showing humans information presented on many different kinds of networks with different amounts of local environmental complexity. And what we find is that when humans are sitting at a point in a network where there's only 1 possible outcome, their reaction time is really swift. In contrast to what happens when they're sitting at a place in their environment where there are 14 possible outcomes, their response is very slow. And we can plot these data points along a line here, and that line indicates to us that humans are processing 1 bit of information in 32 milliseconds. And that, I think, is just sort of fascinating that we take such a short period of time to process 1 bit of information in our environments. But it also more generally indicates that humans are very sensitive to local environmental complexity and respond in kind. But it seems that humans are not just sensitive to local environmental complexity, they're also sensitive to the shape of their environment. And to show you that, I wanted to illustrate for you 3 different kinds of networks that we've had people learn on: a modular graph, which you're seeing on the left-hand side, a lattice graph, which you see in the middle, and then a random graph, which you see on the right-hand side. And what we find is that humans respond most swiftly to the modular graph, respond less swiftly to the lattice graph, and even slowest to the random graph. And so together, those results suggest that humans process information beyond entropy or the sort of environmental complexity locally in their world, and in a manner that depends systematically on the shape of the network or the network's topology. It also suggests to us that perhaps there are some networks that we could and should be using for more effective communication. For example, this modular network, which seems to be quite easy for humans to learn. Now, to motivate the next little bit of this story, I wanted to read you a passage from Arthur Benson's Ruskin, A Study in Personality, where he says, you know how most of us in idle moments, or perhaps even more in moments when we are officially supposed to be occupied, lapse into a reverie in which a stream of thought, it may be placid, it may be vehement, sweeps through the brain from the flushed reservoir of the mind. Suppose you check yourself suddenly in one of these reveries. Try to put down in words what you have been thinking of and as you thought it. You will find it to be ludicrously impossible. Half the thoughts have passed without clothing themselves in any vesture of word. One thing has suggested another, often enough by some trivial similarity of superficial form. The whole thing is evasive, elusive, and irrecoverable. So what is happening in humans' minds as they are performing one of these sort of network learning experiments and building a model of their world? Is it something where they are very accurate, or do they process information in a bit of a haphazard way, with some pieces of information flowing past them without being recognized and other pieces of information becoming central to their model? To answer that question, we want to think about what's happening in the human mind as they're seeing the world. So here is a human who's experiencing the world as some series of events, and in order to build an expectation or an understanding of the network around them, they have to both acknowledge what's in front of them, so the stimulus x at time t+1, but they also have to remember what happened immediately prior, so this x of t in red. If they can remember what immediately happened before and see what's currently happening now, then they understand which events follow another. They're understanding the transitions. And this is somebody who has a relatively accurate memory. But we're not all perfect, and some of us may have more of a fuzzy memory, or have an error in memory, a distraction that takes us away from the current events around us. And in that case, we may remember something in the far distant past as what just happened, and sort of not have encoded anything that happened in the recent past. So this is what we would call an error in memory, or a fuzzy memory. And what we posit is that humans attempt to do 2 things. They attempt to have an accurate model of their world, but that requires high computational complexity. And that sort of trade-off, how can I maximize the accuracy of my model but use as few resources mentally as possible, creates what's called free energy model of people's internal representations of their events. And people may perform this trade-off differently. Some people may prefer more accurate memories and allow themselves to use a lot of mental resources, and others may prefer less accurate memories, allow themselves to use less mental resources. So let me give you sort of a picture of what that means to complement the little bit of math. So here's a person who has no memory, and they're minimizing mental resources and creating models of their world. They anticipate that anything in the past could have been the precursor of what they're currently seeing, and so they build a model of the world that's a fully connected network. Any event could lead to any other event. I want to contrast that with a person who has perfect memory, so their memory of the past is a delta function just on 0, which happened right before. This is a perfect memory, but it also maximizes mental resources. Their understanding of their world is completely accurate. They build a perfect model of their world. And then there's the person in the middle. This is somebody who has fuzzy temporal memory, where they remember things in the past not perfectly, but they tend to remember something recent as what's driving what they're currently seeing, rather than something in the far distant past. In this case, the humans have a fuzzy version of the true model of the world. In other words, they never really see the truth, but they see something that's close to the truth. And this poor memory person is the person who we actually see most often in our experiments. The large majority of people fall into this middle bin. Very few people fall into the no memory bin or the perfect memory bin. So most people never really see the world accurately. They see it in a fuzzy way. So obviously, once you've built a theory like this, you want to estimate the parameters from data, validate the mechanism, and then use the theory to make a prediction about a new experiment. We do all those things in the paper, which I've noted at the bottom of the slide, and they help us to understand why humans prefer this modular network instead of the lattice or the random graph, and they provide a lot of insights into how we can better fine-tune our communication with one another to maximize learning. But I wanted to leave you with one last big idea, and I wanted to motivate it with Joseph Glanville's The Vanity of Dogmatizing, which he wrote in 1661. And in that book he writes, "But how is it, and by what art, doth the soul read that such an image or stroke in matter signifies such an object? Did we learn such an alphabet in our embryo state? And how comes it to pass that we are not aware of any such cognate apprehensions? That by diversity of motions we should spell out figures, distances, magnitudes, colors, things not resembled by them, we attribute to some secret deductions." And from this passage, it makes me question is, how is it that we use our soul to read that such an image or stroke in matter signifies such an object? What images and strokes do we use? We use symbols. We use letters. We use sounds. We use movements of our bodies that create symbols that communicate with one another. How does that all happen? How do we recognize that these symbols in writing or in movements mean something? And I think that motivates a question of how do we actually use communication systems between ourselves? How do we perform information processing with the real networks like language? And so to answer that question, we moved into studying a few common examples of human communication systems to ask whether these simple laboratory experiments provide us with some insights into how humans actually communicate. And we studied in this context language networks, which were word transitions in Shakespeare, Homer, Plato, Jane Austen, William Blake, Miguel de Cervantes, and Walt Whitman. We also studied social relationships as a very important conduit for communication. And we did that through studying Facebook architecture, some science social networks in high school relationships, adolescent health, jazz clubs, and karate clubs. And then lastly, we studied a set of communication systems through music. And in this case, we're studying note transitions. So how does one note transition to another note? And what is the architecture or shape of that note transition system? We do that with works from Michael Jackson, from the Beatles, from Queen, from Toto, and then from several different classical pieces from Mozart, Beethoven, Chopin, Bach, and Brahms. And the question that we're trying to ask is, how much information are humans perceiving from these communication systems? And we break it down into two pieces. The first is they're perceiving the entropy or complexity of the system. We talked about that earlier. How complex is this network, both the local environment and the global environment? But also, now that we know that most humans don't really ever see the truth, they see some fuzzy model of the truth, we want to know how divergent the human's perception of the network is from the true network. And our hypothesis is that human communication systems likely minimize the discrepancies between the truth and what humans see. In other words, their architectures are constructed in a way that's forgiving of human biases. So is that really true? Well, to walk you through the data, what I want to show you here is along the x-axis, the entropy of the real system, and then the entropy of a random system of the same size. The gray line that you see here along the diagonal is the unity line, so that means that you would have the same amount of entropy in the real network as in a random network. What I want you to notice is that all of the colored data points are below the unity line. And what that means is that all of these communication systems have more entropy than expected from other random systems of the same size. And that makes sense. These are systems that are designed to communicate large amounts of information from one human to another human, or from a collection of humans to another collection of humans. So packing in a lot of information is sort of par for the course here. Now I want to draw your attention to the right-hand side of the slide, which is the discrepancy or divergence between how humans would view these networks and their reality. So how distinct are these two? Along the x-axis is the divergence of the real system, and then along the y-axis is the divergence of a random system of the same size. Again, the dashed gray line along the center is the unity line, and all I want you to notice is that all of the colored data points are above the unity line. And what that means is that all of these systems have less divergence between the truth and our perceptions than would be expected in a random system of the same size. In other words, these systems are relatively forgiving of errors in human memory, fuzzy temporal integration, and other related biases of perception. Interestingly, each of the systems differ in how well they do that. So this is the exact same data I showed you on the previous slide, but just reorganized so that you can really see what's different about language as compared to music. As you can see on the left-hand side, where language is in these blue colors, it has a lot of entropy, the most entropy of any of the systems that we studied. In other words, language has extensive complexity. It packs in a ton of information into a short period of space, meaning time. And contrast that with music, which is over here on the right-hand side in the purple colors. And what you can see in music is that the amount of entropy is actually quite low. What that means is that there's less information there. And we think that that's perhaps the case because music is used as an entertainment system as well as a communication system, and that entertainment may be easier or more enjoyable if it has less information content. We can also notice that the music networks tend to have more divergence from expectations than the language systems, and what that could indicate is that there's a lot of surprises in music, a lot of novelty, and perhaps that's something that's important for entertainment systems and less important or less useful in language systems. So these differences between our communication systems, I think, are interesting and motivate future work in this area to understand why different communication systems might show these differences in complexity as well as in the degree to which they are forgiving of our human biases. So with that, I'd like to summarize what we did over the last few minutes. We first learned that humans can learn the architecture of networks underlying continuous streams of information, and humans display expectations about the network that diverge from the truth, but allow them to sort of see this larger scale structure and being sensitive to whether the structure is modular or random. These biases in learning and large-scale perceptions can be explained by a poor memory or by fuzzy temporal integration. And real networks, such as language and music, fit our biases, so have low divergence from our expectations while packing in a lot of information or having high entropy. And what this set of results makes me think of is that, here we are as humans with this amazing network inside of our minds, composed of billions of neurons and trillions of synapses. This network inside of our minds is attempting to understand and learn the networks in the world around us. So in other words, it's almost as if the networks are thinking themselves. And that's reminiscent of this passage in Aristotle's Metaphysics where he says, "Mind thinks itself because it shares the nature of the object of thought, or it becomes an object of thought in coming into contact with and thinking its objects, so that mind and object of thought are the same." With that, I'd like to give you a pictorial representation of what we did over the last few minutes. We started with Hanrein Poincaré. We moved into network learning experiments. We transitioned across Arthur Benson into network learning theory, and then transitioned across Joseph Glanville into human information processing, all to help us to understand how humans build network models of our world. The work was predominantly led by Liz Caruza, who's now an assistant professor of psychology at Penn State University, Dr. Ari Khan, who's a neuroscientist, now a postdoc at Princeton, and Dr. Chris Lynn, who's a physicist, now a postdoc at CUNY Princeton on a JSMF fellowship. With that, thank you so much for listening, and I'd be happy to chat more.
I'm not appearing. Thank you both. I actually don't see myself from the screen. Do you see me?
Yes.
Yes.
Oh, okay. I just don't see myself. Thank you for wonderful talks putting together. I think we have some time that for question and answers that I will monitor Q&A questions, but before we go there, let me ask you a general question. This is really about how each group of scientists perform data analysis or build a model. So Danielle, being a scientist, you first discover how worlds are interrelated and formulate mathematical models beautifully. And then through experiments that you verify the model and then go from there. On the other hand, Sandra, like us, most of the data scientists, what we do is that we use the machine learning tools and we explore and find how worlds are connected through data and try to make a conclusion. And obviously, often is observational study. We often face challenges for lack of causal evidence and also couldn't reproduce or replicate the results. I wonder that could each of you please address the differences, the fundamental differences between, going experiment, controlled experiment, and observational study?
Do you want to start, Danielle?
Sure, yeah, I'd be happy to. So my talk was divided into 3 different sections, and the first one was definitely experiments with human participants. The second part was building a mathematical model, and then the third part was scraping data from the web. And so that was sort of the more typical what you would describe as data analysis. And so I think what I'm really interested in is understanding that the laboratory experiments provide you with really beautiful constraints. Everything is perfect. You can try to define all of the necessary variables involved and tweak them as necessary. The mathematical model brings you understanding because then you have a theory that organizes all of your experimental data in one framework. And then I think going to data analysis of things that you can just scrape from the web can tell you something about whether your mathematical model and your laboratory experiment are relevant to the real world and not just something that happens inside of a lab. So I think that last step is really crucial for us. Sandra, what do you think?
Yeah, I mean, I think identifying cause and effect with observational data is a challenge, right? So I think ultimately what you want to do is triangulate what different research designs can bring to the same question, and the limitations of one can be strengthened by the strengths of another method. The reason why I'm so attracted to observational studies is because ultimately I'm interested in learning what people do in the real world. In the social sciences, we relied for a long time on self-declared information about things like news exposure, right? So how often do you consume news? And people are really bad at giving accurate answers sometimes, and definitely when it comes to measuring their daily exposure to information. And this is what observational data allowed us to do more accurately. But of course, at some point, you also have to ask people questions if you really want to understand their motivations and why they do what they do. And observational data doesn't really give you that much information about that. And so for the study that I discussed in the video, the most important limitation is that we can't really assess whether any of the exposure to bot-generated content had any effects on opinions and behavior, right? Sort of outside of Twitter. And so in that respect, it's important to try to complement studies and as I said before, the strengths of different research designs so that we can give a more accurate and more comprehensive answer to the question. But in this, I think paying attention to observational trace data is important to understand what happens in the real world, but that shouldn't be the only thing that we do, obviously.
Well, so it sounds that Danielle is really doing a combination of the two, and Sandra, I assume that you might once in a while also conduct experiments to really impose some intervention. Do you do that in your lab?
I didn't really talk about it in this talk, but I think the key for the sort of research that we do in my group is try to forge more collaborations with the industry so that we can do some of those A/B testing kind of studies to understand how changing the policies that govern platforms like Facebook or Twitter or YouTube, how that impacts the way in which people behave on those platforms. And this is something that, there's projects on this regard that I can't really talk too much about yet, but yes, the answer is yes.
Thank you. So back to Danielle. I'm also by training is really in mathematics, and I see beautiful mathematics there. And there's a theory and there's application. So it's really enjoyable to see your work. I have one question. It's a little bit more practical. That earlier you have demonstrated the relationship between the complexity of the knowledge and how much they can be efficiently passed to the audience. And there's characterizations about how you really organize your knowledge. My question is a bit of realistic. How do you have any follow-up study? How would this help us as instructors or teachers to better design our lectures and deliver more efficiently to our audience?
Yeah, I think that's a really great question. So in a couple of our studies now, we've consistently seen that a modular organization seems to be more easily learnable to human subjects than any other architecture that we have tried. And so those studies suggest to us that having a lecture that is organized in a modular way is important for information transmission. But I guess I would say that is generically true for the sort of average student or the average listener, the sort of typical person, whatever typical means. But I also think I'm fascinated by the fact that some people prefer to have information presented to them that's quite different than a modular graph. And so ideally what we'd like to do is to understand how does each student learn, not just are they a visual learner or are they an auditory learner, but what are the architectures that they find most engaging and most easy to understand. And so we're doing a lot of work right now in probing sort of just intrinsic curiosity in people. What kinds of networks do they build when they're just browsing Wikipedia by themselves? And then what we want to do is to link that to how they respond to architectures in a lecture. So the idea is that their browsing patterns in solitude may relate to their preferences inside of a lecture setting. So those are open questions we're investigating right now.
I see. So thank you. I really have quite a number of questions from myself that I think I will just email each one of you. And before we leave here, I have one more question to both of you. For a young audience, especially students sitting in front of us, I think the general question is that how to become a good data scientist. My question is also sort of, I'm struggling, right? As a student, should they majoring in some field while accumulating statistics or machine learning skills, or just like me, right? Started mathematics and statistics, but then I found it very awkward now that I don't have a deep knowledge in a particular field. Could you please give the students some advice? What do you think?
Well, in my case, in hindsight, things seem to make a lot of sense, but it's not that I plan any of the steps in my trajectory, to be totally honest. So I think I would be lying to say, it does work to do interdisciplinary work. I mean, I think Danny would also agree that we don't necessarily have like conventional trajectories in the sense that your PhD is in one thing and then your postdoc is in another. I do believe in interdisciplinary work. I mean, I've learned the most working in interdisciplinary teams, and I think, I'm fully in favor of encouraging that, regardless of the risks in terms of institutional affiliation. At some point in the US in particular, there's a lot of emphasis on tenure lines. You have to demonstrate that your research, if you go into academia, you still have to demonstrate that your research is relevant for a particular discipline, right? And so you have to have a home. But I do think that you bring more to that home when you take a more interdisciplinary and diverse training and background. And so I would definitely encourage it. Danny, what do you think?
Yeah, I mean, I think that there's important room for both kinds of people. The person who focuses on mathematics and statistics and then collaborates with domain experts, and that's key, is just to make sure to collaborate enough with the domain experts that you can that you can create a question that's meaningful and interpret the data in a meaningful way. And there's also room for people who are, trained in the domain specifically and then add data science later in their career. So I just think there isn't a right way. The goal should be just to make sure that the questions that are being asked are important and thoughtful, and that you gather the expertise around you that's needed if you don't have it yourself.
Well, so that is very helpful, and thank you both again for wonderful talks, and at least that we give the audience opportunity to get know what you're doing. I guess the time is out. On behalf of the WiDS 2021 team, thank everyone for attending. And please complete the survey at the close of the event so that there's a bonus for that. So you can get hold on slides of Sandra's and Danielle's. And also hope to see you in GatherTown networking. And don't forget, for example, tune in tomorrow to hear our students and Professor Eric Brodlow, Vice Dean of Analytics at Wharton, is going to kick off that event. Thanks again, and we hope to see you next year. Thanks, both Sandra and Danielle.